Sliding down the rails. A metal bar with length capital L, mass m, and resistance capital R is placed on a frictionless metal rails that are inclined at an angle phi above the horizontal. So these are metal rails inclined at an angle phi. Magnetic field is downward. The rails have negligible resistance, so there is only the resistance of this metal bar. A uniform magnetic field of magnitude B is directed downward as shown in figure. The bar is released from rest and slides down the rails. So it is released from rest. Part A is the direction of the current induced in the bar from A to B or from B to A. So as you can see here, we have magnetic field in the downward direction. So if I draw my coordinate axis here like this, as z is coming out of the page, x is inclined with respect to the horizontal axis at an angle phi. Since as the bar slides down the rails, you can see that as it slides down the rails, the flux through this conducting loop is decreasing. So what is that flux? First of all, the flux is phi b is equal to b cosine phi a. So that's the perpendicular component of the magnetic field with respect to this tilted plane. So this is basically b cosine phi times the area of this loop. So the loop has area A. So since as the bar slides down the rails, that flux phi b is decreasing in time. So we see that the flux in this direction, which is the flux density, because the flux density is in minus j hat direction, the flux is decreasing as the area of the loop decreases. So because we have a time-dependent area here. Okay. So according to Lenz's law, a current must be induced that generates a magnetic flux density in a direction that opposes the decreasing flux. So the magnetic flux density created by the induced current must be in the same direction as the magnetic field B. So this should be in minus j hat direction, opposing the decreasing flux density in minus j hat direction. So how is that possible? Using the right-hand rule, you can see that if the current flows from A to B and it follows this loop here, the right-hand rule tells us that the four fingers curling in the direction of the current, the thumb points downward. So that means I flows from A to B. That's the answer to this question, because the flux through this loop, the area is decreasing in time. That means the flux is decreasing. So we need a flux density, generated flux density, that is also downward, in the downward direction, or in minus j hat direction rather, so that we have this flux b cosine phi times area A being compensated for. This decreasing flux is compensated for, and you can see that if the current flows in the clockwise sense as shown here, looking from the top, if the current flows from A to B, the generated magnetic flux density will be in minus j hat direction due to this current, and that will be opposing the decreasing flux. Part B. What is the terminal speed of the bar? So you can see that because we have an induced current here, this induced current flowing on this wire and the magnetic field causes a magnetic force on the wire, which is F sub B, that's equal to I L cross B. And you can see that the L vector is in this direction, which is basically in k hat direction. L vector is in k hat direction. The magnetic field vector makes an angle phi with respect to minus j hat, and with respect to minus I hat, it makes an angle 90 minus phi. So you can see that the L cross B will be equal to I capital L B sine of the angle between them. So if I need to find the perpendicular component with respect to the L vector, so that's basically, that means I need to consider B cosine phi. So B cosine phi is going to be pointing in this direction. The L vector is in plus k hat direction. So it's going to be ILB cosine phi. That's the magnitude of this magnetic force. Or I can say that this L vector is capital L. It's coming out of the page. So this is my z-axis here. This is my z-axis coming out of the page. L vector is capital L in k hat direction. Magnetic field is minus B cosine phi j hat minus B sine phi I hat. So if you look at L cross B, we have minus B cosine phi k hat cross j hat, and then we have minus, of course we have an L here, minus BL cosine phi k hat cross with j hat, and then we have minus BL sine phi k hat cross I hat. So this k hat cross j hat, once again we can use the cyclic permutations. I hat, j hat, I hat, j hat, k hat, that's the positive direction. So the first term, k hat cross j hat, k hat cross j hat, gives us minus I hat, and then we have k hat cross I hat, k hat cross I hat gives us j hat. So we can see that this magnetic force FB is I L cross B, which is equal to minus BL cosine phi in minus I hat direction, where the minus BL cosine phi k hat cross j hat is minus I hat. So we have minus BL cosine phi minus I hat, minus signs will cancel, it will be plus I hat direction. And then we will have minus BL sine phi minus BL sine phi in j hat direction. So what is j hat direction? So because of the minus sign here, this is in minus j hat direction. So that force is basically a downward, which will be balanced by the normal force. So basically what we have done here is to look at the component of the force on the xz plane. So this is basically the component of the force on the xz plane. Okay, or on the x-axis. All right, so as you have noticed, this magnetic force has a component on the x-axis. It has a component on the minus j hat direction, which is balanced by the normal force. So it's only this component we need to worry about, which is basically BL cosine phi in I hat direction. So this will be balanced by the weight of the bar, which is Fg, which has a component Fg cosine phi in minus j hat direction also. So that will be compensated by the normal force as well. And then it will have a component. So let's clarify that. This is Fbx here. And here we also have an Fby. And the y component of this gravitational force is balanced by normal force. The x component, Fg sine phi, will be balancing the x component of the magnetic force. So we will see that we have Fbx, which is ILB cosine phi, equal to mg sine phi at equilibrium. So this is when the terminal speed, V terminal, is reached. Okay, now the induced EMF epsilon divided by the resistance R is the current. So epsilon over R, LB cosine phi is equal to mg sine phi. So here the current is the induced EMF epsilon divided by R. So we can see that the induced EMF epsilon, on the other hand, is L V terminal cross product with the magnetic field. This is basically going to be the motional EMF on this bar. And therefore, if I look at the terminal velocity vector, V terminal is minus V terminal in I hat direction. But at the same time, the magnetic field B is, remember, minus B cosine phi j hat and minus B sine phi I hat. Okay, so what is V cross B then? I hat cross I hat is 0. So V cross B will give us I hat cross j hat, which is in k hat direction. So we will have, for the epsilon here, B V terminal L cosine phi, because V cross B will give us this I hat cross j hat is k hat, and cosine phi term here. This term doesn't give me any non-zero answer. So that's the motional EMF induced. And therefore, I can write, if I go back here to this force equation at equilibrium, B V terminal L cosine phi divided by R, that is the induced EMF, L B cosine phi is equal to mg sine phi, and that gives me, for V terminal, capital R mg sine phi over cosine phi is tangent phi divided by b square L square cosine phi. So we have calculated the terminal speed of this bar. Part C, what is the induced current in the bar when the terminal speed has been reached? Okay, so in part C, we have the x component of the magnetic force, which is ILB cosine phi, balancing the x component of the gravitational force, mg sine phi. This is when the terminal speed has been reached. Therefore, the current from this equation turns out to be mg tangent phi divided by BL. That's the induced current. Let's move on to part D. After the terminal speed has been reached, at what rate is electrical energy being converted to thermal energy in the resistance of the bar? The power is rate of energy I square R. So we know the current from part C. Therefore, we will have m square g square tangent square phi r divided by p square L square. That's the power. Now let's move on to part E. After the terminal has been reached, at what rate is work being done on the bar by gravity? Compare your answer to that of part D. So let's do that here. So this is part E. Now the power due to the gravitational force is the gravitational force dot product with the terminal velocity, V terminal. So this is going to be mg sine phi V terminal, obviously. And I know what the terminal speed is, so this is going to be equal to mg sine phi. The terminal speed was found in part B, capital R mg tangent phi divided by b square L square cosine phi. And if I rewrite this as my final answer, it's going to be 2 m's and 2 g's, so m square g square. So I will have m square g square tangent square phi r divided by b square L square, because I have a sine phi over cosine phi, that will make this tangent square phi. That's the power. What was the power I have found in part D? M square g square tangent square phi r over b square L square. It's the same. So I noticed that the power due to gravitational force is the power that is consumed by the resistor. So that's the energy being converted to thermal energy in the resistor. Okay, so in this problem, I have a bar, a conducting bar that is sliding on these metal rails. The flux density is basically B cosine phi multiplied by the area, and since the area is decreasing, this flux into the in the minus flux density in the minus j hat direction is decreasing, so we need to have a current, induced current that induces a magnetic flux density in minus j hat direction, which is basically achieved by a clockwise rotation. The right hand rule tells us four fingers curl in this direction, the thumb points in minus j hat direction. So that's basically the sense of the current. That's a clockwise rotation. So current flows from A towards B. Now, what are the forces acting on this bar? There is the magnetic force IL cross B, where L vector is in the direction of the current, so L vector is L k hat, so that's the z-axis coming out. And the magnetic field B is pointing downwards, so that's minus B cosine phi j hat and minus B sine phi I hat. So L cross B gives us two terms, which are BL cosine phi in I hat and minus BL sine phi in J hat. So the minus J hat component will be plus the minus J hat projection of the gravitational force balanced by the normal force. But on the other hand, we have the x component of this force, which is FBX here, that is due to this term, BL cosine phi, and that will be balanced by the x component of the gravitational force, which is mg sine phi. So these two will be balancing each other. And the magnetic force IL cross B is epsilon over R, that's the current, LB cosine phi, which is mg sine phi. Now, what is the induced EMF? It is the motional EMF, L magnitude of V cross B. The terminal velocity is in minus I hat direction. The magnetic field has a minus j hat and minus I hat component with this new coordinate system. So V cross B gives us I hat cross j hat, k hat, V terminal B cosine phi. So V terminal B cosine phi is the magnitude multiplied by L gives us the induced EMF. And induced EMF divided by resistance gives us the current. Current LB cosine phi is mg sine phi. From this equation, I can find the terminal speed. And what is the current then? The current is mg sine phi over BL cosine phi from this equation at equilibrium. So I is mg tangent phi over L. The power, basically the rate of energy conversion from electrical energy to thermal energy in the resistance of the bar is I square R, as we have found here. And comparing it to the terminal, the rate of work being done on the bar by gravity, that is the dot product of force with velocity, we see that it's the same. So this is the rate of work being done on the bar by gravity, and which is equal to the rate of energy consumed by the resistance. So the electrical energy is being converted to thermal energy in the resistance, but there is also work being done on the bar by gravity. So basically these two powers are the same.